we are going to start with an interesting question. The question is, the end statement in a list of 100 statements is exactly n of the statements in this list are false. What conclusions can you draw from these statements? Here, there are 100 statements, and the first statement is going to be exactly one of the statements in this list are false, and so on. So the 100 statement is going to be exactly 100 of the statements in this list are false. We have to note that there are only 100 statements. Okay, so what will be our initial observation? Initial observation will be that at most one statement is going to be true. Not more than one statement among these 100 statements will be true. If more than one statement is true among these 100 statements, let's see what is going to happen. Suppose the ith statement and the jth statement happen to be true. Ith statement is going to be like exactly I of the statements in this list are false. And the jth statement is going to be like exactly j of the statements in this list are false. And I is different from j because they are all distinct. We can't have exactly I statements false and exactly j statements false when I is different from j. So that is impossible. So the initial observation is that at most one statement is true. Now, what about zero statement true? Which means, what if all of the 100 statements are false? Can that happen? That is our next observation. Suppose if all of the 100 statements are false, which means all of these 100 statements are false, right? And now look at the 100th statement in our list, which says exactly 100 of the statements in this list are false. And that is true because we assume that the 100 statements are false. When we assume that, we get that the 100th statement is going to be true. So it is not the case, which means that exactly one of the statement among these 100 statements is going to be true. That is our second observation. Now we need to find out which statement is true among these 100 statements. Suppose the first statement is true. Let's see what the first statement says. Exactly one of the statements in this list are false. When we assume that the first statement is true, it says that the 99 statements are true. But that is not the case. Hence, the only one statement which is true from this list is not the first statement. That is clear. Only one statement is true. Now, if you go on like that, take a look at the 99th statement. 99th statement says that exactly 99 of the statements in this list are false, which is true, right? Because only one statement is true. The rest 99 are false. And hence, the 99th statement is that statement which is true and the rest of them are all false. This is the conclusion that we make from these 100 statements. Now let's see what is a tautology, contradiction and a contingency. A compound proposition that is always true, no matter what the truth values of the propositions that occur in it, is called a tautology. A compound proposition that is always false is called a contradiction. A compound proposition that is neither a tautology nor a contradiction is called contingency. So, P or not P is a tautology. P and not P is an example of a contradiction. P or P is an example of a contingency. Compound propositions P and Q are called logically equivalent if P if and only if Q is a tautology. Let's see why we say that if P if and only if Q is a tautology, then P and Q are logically equivalent. Let's see. If P if and only if Q is a tautology, which means that for all the possible values of the proposition that occur in it, P if and only if Q is going to be true always, no matter what the values of P and Q are. Now, when P if and only if Q is going to be true, we know that when P and Q both have the same truth value, then only P if and only if Q is going to be true. Hence, when P if and only if Q is a tautology, which means that P and Q are always having the same truth value, and hence P and Q are logically equivalent. Let's take a look at the De Morgan's law. Not of P and Q is equivalent to not P or not Q, and not of P or Q is equivalent to not P and not Q. See what is happening here. Not of P and Q. So we are bringing not inside of the bracket. So not of P is not P. Not of and is going to be or. Not of Q is not Q. That's why not of P and Q is equivalent to not P or not Q. And now not of P or Q. Again we are bringing the not inside. Not of P is not P. Not of or is and. Not of Q is not Q. And hence not of P or Q is equivalent to not P and not Q. Another popular logical equivalency among conditional statements is that P implies Q is equivalent to not P or Q. Again, using truth table we can verify. So when P implies Q is equivalent to not P or Q, which means that they have same truth values for all possible cases, right? Now let's look it intuitively. P implies Q is going to be false only when P is true and Q is false. Now let's see not P or Q. Not P or Q says that P is false or Q is true, right? So not P or Q is going to be true when P is false or Q is true, right? And not P or Q is going to be false when P is true and Q is false. The negation of it. Negation of not P or Q is P and not Q from De Morgan's law. And P and not Q means P is true and Q is false. That is a negation of not P or Q. And that is exactly same as P implies Q. Because P implies Q is going to be false only when P is true and Q is false. These are some of the logical equivalences involving conditional statements. These are some logical equivalences involving biconditionals. Now, here is a question. Is propositional logic adequate enough to represent the meaning of statements in mathematics or in natural language? That is, can we represent all mathematical statements using our propositional logic? Is it possible? Think about it. In the next video, we are gonna see predicates and quantifiers.